Okay, well, hello, I'm John Cerrucci, and tonight we're going to talk about GIS, a general introductory overview. I've actually done this presentation a couple times to different groups with different interests, but tonight we're going to talk about its application for Engineers Without Borders projects and with some specific examples from what we've done here with the Lehigh Valley professionals. So, you all have maps on all your devices and probably have looked at 3 or 4 maps today to check the weather or maybe get directions to this place. And we've kind of taken them for granted, although you've obviously noticed that they've changed a lot in the last 10 years or so. First of all, you carry them with you pretty much everywhere. You're connected. And they're doing things. And in fact, sometimes the maps don't even look like maps. So here's Brockville Middle School. That's not a photograph, that's aerial imagery that's draped over a digital elevation model and rendered in 3D. And that's all kind of done in the background. And if you go out to Google Maps 3D, it's doing it in real time as you move around. So that's a map. That's what maps have become right now. What we're going to be talking about tonight is what's behind the maps, and that is the GIS that powers them, and the other things that it can do besides make 3D pictures of high schools and middle schools. So before we get all caught up with our species about like being really great with maps and stuff, I think it's important to understand is that we relate to maps because we're wired that way, and we're not the only organisms. Many animals, birds migrate south, and ants follow pheromone trails that they've laid down. Bees have some kind of dance to tell each other where the food source is. Talking Disney animals find their way home. So it's in our wiring. This spatial awareness and our neurological structure really has the capacity to think about space, where we are in location. What we can uniquely do as humans, though, is we can make maps and relate to them. And we've been doing it for a long time, and probably I would suggest that this is probably the oldest model that humankind has ever used. Very likely tens of thousands of years before that Babylonian map was made, somebody drew a picture in the sand of where something is they wanted to get to. So they've been around for a long time. They do different things right now, though. They are interactive. They talk to us. Usually, really, the map is a data interface, and we're trying to get information or learn something from it, and we're using it as a visual because we understand it. But the underlying information is, how do I get there, and what's the traffic like, and maybe a number of other things, which we'll talk about tonight. So I'm going to go back a little bit. This is like a 3-minute history of GIS, something that's kind of at least characterized as maybe the first documented example of a geographic information system was related to a cholera outbreak in London in the mid-19th century. And at that time, this is before modern germ theory, and no one really knew what caused cholera. They thought it was bad air or something like that. There was a doctor, John Snow, who, something about this. John Snow, who hypothesized that it was a waterborne vector. And when this particular outbreak happened on Broad Street, he decided to try to find some evidence for that. So he mapped out all the cholera cases. One nice thing, particularly in city areas, there's usually very good maps because the insurance companies were very thorough cartographers in terms of keeping track of where everything was. So he mapped out the cholera cases and where the town pumps were located. And as soon as that was done, it was very evident. There was a bullseye pattern that said this is the central point for all these cases. That well was disassembled and the epidemic, the outbreak ceased. So it was really tangible evidence based on spatial analysis of what the cause of a disease was. And in that respect, it was a medical milestone. So when we talk about a GIS, that means a Geographic Information System. It's in the geography world. It's in the kind of like the geeky corner of it. So geography is all kinds of cultural stuff, and of course the physical geography that we're kind of familiar from grade school. GIS is really where geography meets IT. when we say GIS, what is it? Well, it's kind of an abstraction, but this graphic kind of describes more or less what it does. When you have a particular type of data that is geo-referenced, that it has a location assigned to it, you compile that into a database which characterizes that location. So it's a relational database. And that database is organized based on these spatial references. And with that, then, you can extract information and perform many methods upon that data because of its arrangement in this spatial relational database. And a lot of what that is data visualization, which is another way of saying maps. So you make things that you can look at. But you can also query it, extract information, filter, look at trends, do statistical stuff, look for patterns and relationships. And that's really what GIS is all about. And it's become a discipline. So I don't know whether it's really a science or it's an applied science. It's not fundamental. But most of the people who practice GIS are folks that have picked it up. They have some other area of subject matter expertise, and they need GIS tools to get their job done or do their research. There is a core group of people who have focused this primarily. I'm sort of a hybrid. Okay, I'm a career chemical engineer, and I happened to get some formal GIS training late in life because it was pretty cool. And okay, not going through this, but of course, there's many, many different aspects to this. There's the heavy-duty IT piece for the developers. I'm kind of into my own interests are in analytical methods and modeling work, spatial analysis. But certainly it starts with making maps. I mean, maps are not made anymore by somebody sitting down on a table there and getting ink out and drawing them out. GIS is the engine to make modern maps, and certainly interactive maps, which we're becoming most familiar with. One of the reasons that GIS has exploded is because of the availability of data. I mean, it's just mind-boggling how much information is out there, and you've all heard about big data. A lot of that big data is spatially referenced. It has a location, so that makes it useful in a GIS. And it comes from many places, from the field still. That's Sean Dooley out in Sierra Leone there. So we ourselves have collected a lot of data on the ground, which you still need to do, but more and more so information is coming in through remote sensing. We have tons of aerial imagery, satellite imagery, and this isn't just pretty pictures. This is multispectral imagery, which can be managed in all kinds of ways to do very sophisticated analysis. Social media is a big source of spatial data. When you're walking around, tweeting, unless you've turned off that function because you prefer your privacy like me, you're telling everybody where you are. And when tens of hundreds of millions of people are doing around the world, you can do some really interesting things with that. Certainly, there's a lot of people doing commercial stuff with that, following trends, looking at marketing. You can use it for emergency response. It's very likely that social media is going to be early warning signs that something's happening, like an Ebola outbreak, long before it kind of gets into traditional channels. So the ability to be able to mine that stuff now is kind of changing the game. The census, is a traditional source of spatial data. I mean, they have tons of information about everybody, and they know where you live. So, and a lot of that is available. Its resolution is sort of purposely reduced so that you don't interfere with privacy issues, but just reams and reams of information that can be used in a GIS from the census. And public and private sources. So it's one of the reasons that GIS has really taken off. The second piece is the IT side of it, computational power, and particularly the fact that that our computers have become mobile now. So now kind of go into the structure of this a little bit. This is either very interesting or very boring, and maybe I'll see who in the audience goes which way here. But one way to think about the way GIS is arranged, not the real way that it's stored in a in a database, but the way that you can think about it, and when you access the way you see it, is as layers. So you have a lot of different kinds of information, which is kind of shown here in this cartoon. It might be land cover, physical boundaries, roads, elevation information. And all that stuff has some things in common. That is, it has a locational reference. So you can imagine that cartoon there. You can drill down through that and find out what's the elevation where this river is or this boundary is. You can relate that stuff based on its organization spatially. And the way that information is saved is in really two general structures, either as vector or raster formats. So vector formats is points, lines, and polygons, you know? I mean, if the city of Bethlehem is a vector point, it doesn't have a space, it's just one place. Usually when you look at a big map, you see a little dot there for a city. Okay, that's a point. However, if you get a little closer and you're in Bethlehem, you might want to consider it as a polygon. A roadway could be a line. And of course that takes away its width dimensions. But so these are simple ways of representing data. It's not particularly good for surfaces. So if you want to look at something that's continuous, you're more likely to look at it as a raster. You can think of that as like a checkerboard grid where you have cells and each one is assigned one value. So that's often how elevation is represented. Or on the temperature maps, when you or the weather maps you see in the morning, that would be raster data. It's modeling a surface or emulating a surface by having discrete cells that have values, and then of course, just like when you're looking at a pixelated image, when you back up far enough, it all kinds of looks like a smooth thing. So both of these things are used. In fact, as I've shown here, you know, you can have the same information represented either way, and you can switch back and forth. A lot of it has to do what you want to do with it. You can also have different kinds of information in the same GIS. And then what it really looks like in terms of file types, the typical things, there's quite a few of them, but one of the most common is a shape file. It's called a shape file. It's actually multiple files, but that's a commercial file format used by ESRI, one of the big players here. GeoJSON, KML you might recognize as Google's file format. There's many others. More and more so it's going towards geodatabases where there isn't really a discrete file and the information is organized in a different way. This is not something that you really have to be concerned about, but just know that it's kind of evolving with the size of the information now, because computational methods are scrambling to keep up with the fact that you want the answer right now. You know, I want to know where Pizza Hut is and whether they're open still, and you want that connected, and so it's going to look at your location and get you there real fast. So the way this stuff is incorporated is important in terms of kind of being able to get at it quickly.
What's ortho imagery?
Oh, well, I'll answer that, though I moved the slide. So the question was, what is ortho imagery? When you fly over the land and take a picture from your airplane, the photographer here knows this, you get a skewed image. You're taking, some things are real close to you because they're right below you, and some things are out at an angle somewhere, and so they look smaller and distorted. And if the land has contours, that gets weird too, because like the top of the mountain actually in your image looks like it's someplace farther away. So when you take when you have aerial imagery, you have to do a lot of processing of it to kind of make it all to scale and put things in their right place. You have to stretch it around, and that's orthorectification. That was a process that used to be done with transparent films and lights and drawings. So there was a kind of a very interesting optical mechanical way of doing this. Now, of course, it's all done through computers. But it's the process of converting that raw information to something that is correct in terms of its relative location and scale. So now we talked about like all these different layers. If you look at just one layer, in this case, the map that I've shown there, those are the locations of waste energy plants in the United States, represented as point vector data. So each one of those locations has a little name label on it, but we can also assign an awful lot of attributes to it. So there's an array that goes along with this layer, and the way it's shown here is the different features. Each one of those individual plants is represented as a row, and then for each one of those, we can assign all kinds of attributes to it. So we can pull in all that kind of information around that point. It's not just the fact that something exists there. We can give it many, many attributes. So you end up with this large, looks like an Excel file. It's an array. And again, another powerful thing with being able to save your data in a way that it's spatially related. Once you have all this stuff, then you have to do something with it. So what do you do with it? Well, first of all, the basic things are, the world isn't flat, and maps usually are, so that's a problem. So you have to project it, and when you project it, you make it wrong. You distort it, because we want to take a surface and flatten it out. So the process of projecting something from the irregular planet to a flat surface is called projection. And it's not just a simple matter of like stretching it out. There's hundreds of different ways you can do it, depending on what you want. You've all seen the map where Greenland is the size of South America, right? Okay, that happens to be a good map, which north and south and east and west are always pointing in the right direction. So if that's important to you, great. But if you want to calculate the land area, it's totally wrong. So you can project maps in different ways based on what you want to do. In all cases, you distort them. I've made this comment about measuring things on Google Earth. You don't give much consideration to projection there, but they do a very simple projection. They basically assume the Earth is a sphere, which is very wrong, but it's a quick calculation. So it allows you to fly around in 3D space very quickly. But again, be careful if you're trying to get accurate measurements for that kinds of things. This is when projections matter. Datums. So where is here? Okay, we might be here, but what does that relate to? So you have to reference this to some place on the Earth. And so a datum is a geometric representation of the planet, which corrects to the extent possible its irregularities. The common one that's used is WGS 84, which has a central reference point in the center of the planet. Until 1984, you couldn't do that because we didn't have satellites up there to do that. So, and it also estimates the irregular surface of the Earth based on a constant gravity line, which counts for lots of bumps and shapes and stuff like that. So so when you just get your coordinates, it's not sufficient. You have to know what datum it corresponds to. Sometimes they're not coordinates too. There's a lot of other coordinate systems other than latitude and longitude. You've seen some of these in some of our projects where you see like UTM 28 or UTM 19. There's just a bunch of numbers that don't mean any sense at all. Or if you want to see something interesting, go out to what3words.com. So this is a company that has mapped the entire world. Every single square meter has 3 words assigned to it, I think in multiple languages. So you can actually get your coordinates based on semantics. So that's the process of projecting, again, which has to be done. The other thing is georeferencing things. So once you've found something you care about, you have to assign it to one of those coordinates. And sometimes you can't just do that because you have your GPS receiver and you get the answer. Sometimes you might have a street address, so you have to convert that to an actual location. That's through geocoding. So then we start doing this kind of database stuff. You go in and get information, do queries, you want to ask it a question, get a piece of information back. We can manipulate the data, we can join these shapes, we can merge them, we can dissolve boundaries, we can look at intersections and features. You start doing things like Boolean operations. So I have these layers, and I want to know where the temperature is above 40 degrees and the grass is green and we're more than 100 feet from a road. And you can basically run those operations across different layers and identify those places that meet that criteria. Feature filtering by conditional values, well, that kind of part of you, just around one feature, you can look at areas that satisfy certain criteria. Maybe we want to put something on a surface, but we want the slope to be less than 5 degrees. So we can extract that information from a digital elevation model. And then often, most common thing done is just distance operations, looking at how far from here to there, sometimes not necessarily on a straight line, sometimes it's over a terrain, or sometimes it's along a river or a roadway. So you can measure things in different ways. Or you do buffers, like, so I have a road or I have a river, I want to know what's around it. So you can look at the buffer region and then query the information within that buffer, like shown here. Okay, then some of the more sophisticated stuff is playing with the statistics. And spatial data is special, okay? That's what it says up there. Something that, well, it's coined as the first law of geography, although I would say it's not a law because I'm a little bit insulted because of my thermodynamic laws, but it is actually kind of meaningful. Everything is related to everything else, but near things are more related than distant things. Okay, I don't know if that strikes you as being very profound, but what it means in terms of statistics is that spatial data is inherently autocorrelated. That's probably better saying it that way. If things are near each other, they have things in common. And so that's an inherent feature you look at when you do statistical analysis. And it's kind of built in. If I'm standing here, probably when I step over here, unless it's a cliff, I'm going to be at a similar elevation. We're all in this room together. We probably have something in common. So when we're not reinventing statistics for GIS, but there's a special category of statistics dealing with that correlation. Some of the things we're commonly going to do is looking at point pattern analysis, okay, or looking at density surfaces. We always have to do spatial interpolation. I mean, when you get the temperature maps or a contour map, somebody didn't walk along that contour and find all the places that were 20 meters elevation. They did sample points, and then they interpolated between them. So that's a very common operation. Then you look at trends on those surfaces. Focal statistics is, okay, something's here. What's 5 kilometers around it? What's 10 kilometers around it? I average that information, look at standard deviations and distribution profiles. You can do fancy stuff, getting to like fuzzy statistics, and that's like, well, that's a different seminar. And cost distance network analysis. So I want to get from here to there. This is what Google does when it tells you the best route. You know, it's not just measuring the distance along the road. It's looking at other things like travel time, speed limit, real-time information on traffic, and it's doing a cost to get from here to there and comparing different alternatives. It does that pretty fast too. So that's what cost distance analysis is. An area that I did my school research in is multi-criteria decision analysis related to GIS. Okay, there's a lot of tools out there. The dominant commercial tool, the Microsoft of the GIS world, is ArcGIS from ESRI. It's a private company. It's been around for as long as GIS has been around, I think since the 60s. They dominate the field commercially. They have a really powerful product. It's a good company. It's not an evil Microsoft. It's a good Microsoft. Very powerful tool. Very expensive for single user licenses. But here's the good news: nonprofits and educational licenses are really, really inexpensive, like $100, and it gives you the full suite. There's other things that do something very much like it. QGIS is a free and open source software that is like the ArcGIS desktop tool. It's not nearly as powerful, but it's pretty good. And if you just wanted to set something up and play around, I would steer you towards QGIS. ArcGIS is also moving to an online platform. As a matter of fact, I expect like in 10 years, that's the only choice, maybe in 3 years. Like a lot of other folks, they're changing their business model. And there's good and bad aspects of that. Their desktop tool is really powerful, still much more capable than the online platform. As that changes, though, I think we'll see everything move to online. I'll just mention a couple of others. So I've talked in the past about OpenStreetMap. It's not really a GIS per se. There's a GIS behind it. OpenStreetMap is sort of like an open source Google Maps. The nice thing about it is it is crowdsourced. So when we've come back from Sierra Leone with information, I've built that out on OpenStreetMap for everyone to go look at. Centennial School is there. So is many of the features in Machete and Cabeza de Toro. So we can put things into OpenStreetMap and get things from other folks. OpenStreetMap tends to have a lot better information about where things are in the developing world than Google does, because the Google car hasn't been to Metro yet, I don't believe.
How do you know it's accurate?
You don't. So you take what you get. And I'll actually show some examples. I'll try to remember to point out what information came from OpenStreetMap. And so in a lot of cases, it was a good start, but then when we got feet on the ground and better information, I could go back and revise it. So that's the good and bad of crowdsourced information. There's also, well, there's a lot of open source stuff. A lot of it is related to web development. So of course, the people that make these real slick maps for your phones and your computers, there's a lot of stuff behind that is constantly evolving, and the open source area is just really fascinating. So many people that are on the developer side of GIS really geek out on this. Okay, so I'm going to just kind of show a screenshot from, this is from ArcGIS Desktop, and I've opened a lot of windows to show things, but you couldn't actually function with it this way. Just wanted to point out some of the features. So right in the center there, you see what looks like a map. And so the way you interact with this stuff is usually through a map, because that's a good GUI. And if you're astute and recognize things, that actually is in the true hospital there. Now, so within ArcGIS, these are all the things you can play with, right? So I have my table of contents. So I've created this, I've put things into it. These are all different features. These are different layers that I've built from the data. It comes from different places. Actually, those buildings started in OpenStreetMap, and then when we got there and got some better information using GPS receivers, we revised it, and I will go back into OpenStreetMap and correct that information, as I've done it for Centennial School. So we have all this stuff. We have waypoint information and things that we've imagined that we're going to build in the future and have drawn in. Contour lines that I'll talk about where they came from digital elevation models. And you can turn this stuff on and off, and of course do things to change the way it looks, which is particularly important if you're trying to see something or maybe make a visualization to share with somebody else. All this is saved in a document file, which doesn't actually save the data. It really just tells you how you want to see the data portrayed. It says, you have all of this information in different places. Here's a representation of this map. I can open that file and get that representation back up again. So I save a lot of those. If I like a picture, a view of something, Bill calls me up and says, let's look at this. I'll click on one of those, add a few things, and save it as another map view, because it takes up very little space. I'm not necessarily adding any data. It's just the framework for looking at it. We can go in, I think I clicked on one of these waypoints, and over here on the left-hand side, this is probably where I should be using the laser pointer here, right? There. Over on the left-hand side, I've just queried one of those waypoints. I think it's one of these in here. Oh, it's over by triage. Must be that one right there. And so now you start to see, well, there's various attributes. When we got that waypoint, loaded it into the GPS, wrote some more information about it. It's the southeast corner of the triage building at the hospital. Okay, and I got a kind of a not very accurate elevation and longitude and latitude information stored where we got it from, what time, probably information about who captured the data. We also, for these features, this is our master waypoint file. We have over 1,000 GPS receiver waypoints for the Sierra Leone project now, and about 350 from Dominican Republic. So every time you guys come back and you have some more stuff, I just keep it in that repository. It all goes in the GIS, so it's a good place to keep all that information. Some of it has more details about it. This last trip, I was able to get a lot of people's phone information. So when you take a picture, unless you haven't turned on that feature, it's the GPS receiver in here is also telling you where you are. So that's basically a data point that we have some information about. And then finally, like across the top here and over here on the right-hand side, there's hundreds and hundreds of tools that do all these things to manipulate the data, test it, draw it in different ways, change it, look at relationships, do tests. And in addition to the ones that are there, it's fairly easy to go in and write code. You don't have to be, a master programmer. You can write Python script in a pretty simple format to make it do things that you want it to do pretty easily. Yes, question?
John, when you take a photo with a GPS-enabled phone, so that it knows where the phone is, it doesn't know where the target image is. Does it also give you directional information of which way you're pointing, or is that not?
Well, that's a function of your phone, and like an iPhone does, because your phone also has a electronic compass in it, and so when I take a picture with this phone, it tells me where I am, but which way I'm facing, and what angle the phone is, and all that kind of information. Now, it might be total crap. I mean, doesn't mean that it's very good. If I'm standing here next to like this doing it, the compass is pointing in the wrong direction. So, but you do get that information. That's a function of the phone. And so, well, you're familiar with the metadata you see. That's where you'd find that. It's a function of the camera or the phone device, whether all that's captured. If it is, though, I'm data greedy, so I pulled all that into the GPS. So I've retained all that information from the cameras. Now the bad news is the phone GPS receiver is really not as good as even a recreational GPS receiver. It looks real good when you're driving down the road, but that's because first of all, Google has figured out if you're going 60 miles an hour, you're probably on the road. So they'll correct you to be where the road is, even if your GPS says you're like 30 feet in the ditch. So it looks real good, and also because you're moving, it's actually doing a lot of data averaging. But GPS receiver isn't so good. This is, but it gets you close. Okay.
It's also a good backup if you don't use the GPS correctly, as I've learned.
Okay, so it's kind of my last general slide on GIS before we dive into some EWB examples. So this is kind of where things are going. I mean, the field is changing very rapidly. You should be aware of that because you see it happening around you. Everyone is interacting with maps in different ways. So things becoming real time, and this is, I guess this is trends. I first made this slide about 2 years ago, and I think most of this is already, oh yeah, been there, done that. Real-time GPS. I mean, you're already doing that with many things. We're going to see much more of that, and part of that is the Internet of Things. So you're connected to stuff, and your phone is one of those things, by the way. So everything that has a location assigned to it, either because it's stationary and you know where it is, or because it has a GPS receiver and it's telling the internet where it is, kind of all gets linked in, and so many people are doing so much more with that. We used to think, I always kind of thought chemical engineering is about like dealing with things that are, nanometers, microns, millimeters, and meters, and GIS starts off with meters, tens of meters, kilometers, and the planet. But truth is, GIS is kind of getting into finer details and resolution, and indoor stuff is being merged with outdoor stuff. Ability to be able to go in and just use laser imaging to get a 3D image of the inside of a building. You'll see more and more of that. I think Google Maps is going to have subways and all that stuff. In indoors of buildings is being mapped now and merged with all this. So that allows 3D GIS. Again, we can see examples of that already here. The crowdsourcing I mentioned too. Augmented reality, which is like really cool. I saw something like that. That picture there with a person with the iPad looking at things underneath the streets. I saw a demonstration. So if you have that information, imagine you're at a process plant walking around and you point it in the right direction. Your device has both a direction and a location, so it knows where you are. But behind that is information around the pipe works and the equipment, what's inside there. And you can look inside the cold box or inside a piece of machinery, push a button, get data. All that is going to just become the way things work now. The domain continues to expand. It's very broad. I mean, GIS covers a lot of things. It is kind of ubiquitous in many, many different fields. And it is moving to the cloud, for better or worse. So that's positive in terms of sharing and interactivity. Of course, it has all the privacy concerns and issues and security issues associated with cloud-based stuff, but it's inevitable. So I'm going to move into some EWB examples now. Any kind of, before we move past that, any kind of general questions about GIS? Yes.
Do you know of any applications that do historical layers? So you could, like that iPad example, would you be able to scan something and see it before and after?
So the question was, are there examples of building historical layers in a GIS? I mean, I'm certainly aware of those. The possibility of doing that is there. So if you have the data, if you have historical information and it's georeferenced, you can absolutely do that. I have seen examples where people have taken like those old insurance maps and rubber sheeted them to get all the projections right and progress them through time. You effectively can see that in Google Earth if you go and pull up historical imagery. So it's photographs, but they are orthorectified and manipulated. So you can look at aerial imagery over a period of time, whatever they have the data points for. In some cases, that's actually pretty useful to see what development is taking place. So I have seen many examples of that. The key is that you have that information. If you have it and it's spatially referenced, you can certainly put it in a GIS and do things with it. Oh, I guess now that I get the laser point, I got to reach.